This last example tends to be to what type of extreme we can take this to. You won't see me give you any of this kind of stuff, at least on the unit exam, but this is the type of question that you could see at the very end of the term on a final exam, or you could see at the very end of the term on a diploma exam. It's bringing together all the concepts that we've done with momentum back in Unit 1 and combining it with what we've learned about photons in Unit 4. So you could see these types of questions, and you saw a little bit of electricity and magnetism combined together in the last unit. You can see that at the end of the term, we could kind of pull these all together, and that's what makes the diploma questions a little bit more challenging, is because it pulls not just one single concept, it could pull things from multiple units. We are going to use for Part A a pretty basic formula just like we did in Example 3, but Part B we're going to have to use conservation of momentum. So what I want to do is just kind of draw the diagram, calculate the wavelength of the scattered ray, and then we'll go through and basically find all our parts and do conservation of momentum for Part B. So we have an X-ray source with an initial wavelength of 1.28 times 10 to the negative 12 meters, is shot directly east at a piece of granite. So I'm just going to use vectors to draw this. I know it's a wave type picture. So it hits an object. It's traveling directly east initially. On the other side, the ray appears to scatter. So I'm just going to draw a little dashed line at an angle of 15 degrees north of east. So there's my angle. So there's my X-ray after. What it's going to do is hit an electron, and it's going to move off at some angle below. We already know, according to conservation of momentum, total momentum before has got to equal total momentum after. And this is our picture. And this is the same diagram that I put in your notes. I'm just drawing it in a vector type method. So I have the initial wavelength. All I want to do is find the final wavelength. Well, this is very similar to what we did in Example 3. We have the angle, so we can use the change in wavelength formula equal to h over mc 1 minus cos theta. Nothing different than what I asked you in Example 3. So it's 6.63 times 10 to the negative 34 joule seconds divided by mass of the electron times speed of light. And again, multiply it by 1 minus cosine 15 degrees. You can see this could get a little bit more complicated if you had to find different parts. But again, you'd use the same formula. You'd just manipulate it for angle, or you'd manipulate it for whatever you're looking for. You'd never solve this for h or c or m, because those are all constants. So if we punch this in again, times by 1 minus cos 15, you should get a change in lambda of 8.266. And again, I don't need to go to right sig digs on this one because this isn't my answer. This is our change in lambda. We know that change in lambda equals final wavelength minus initial wavelength, and what we want to do is final wavelength equals change in wavelength plus initial wavelength. So if we put our numbers in, keep that original on your calculator so that you don't have a rounding error. The original was 1.28 times 10 to the negative 12 meters. It's supposed to be a 14. And I'm just going to write this off to the side here. Plus 1.28 to the negative 12 should give you 1.36 times 10 to the negative 12 meters. There's our final wavelength. We'll carry that to the next part of the question. So again, part A, identical to what we've done before. Part B, we're now going to need to work on some momentum information. Since we want to find the velocity of the ejected electron, what we need to do is we need to do conservation of momentum. So what we have to do is build on the total momentum before equals total momentum after. Well, in the before scenario, we had a photon that was traveling straight east with a wavelength of 1.28 times 10 to the negative 12. So the wavelength, 1.28 times 10 to the negative 12 meters. And it was traveling straight east. So what we can do is find its total momentum. And momentum in this case is going to be equal, when you go back to your data sheet, is going to be equal to h over lambda. So momentum equals 6.63 times 10 to the negative 34 joule seconds divided by the wavelength 1.28 times 10 to the negative 12 meters. So the momentum before, 6.63 to the exponent negative 34 divided by 1.28 exponent negative 12 gives us a total momentum of 5.1797. I'm going to keep this to a few sig digs. 1797 times 10 to the negative 22 kilogram meters per second, and this is straight east. And I'll draw my little picture. I'll use a dot and a vector to indicate that that's its original momentum. The after scenario, we have two things to worry about. We have the scattered X-ray. So I'm going to write the scattered X-ray first. And we know its momentum was at an angle. So we're going to need to break this into X and Y components. We know the angle from the original question was it was 15 degrees north of east. So 15 degrees. And what we are going to need to do is find the Y component and the X component of this momentum. Now the wavelength after we just worked out in part A to be 1.36 times 10 to the negative 12. Now we're going to have to find the resulting momentum, then break it into its X component and Y component using trig. Lots of work involved. Right back to Unit 1. Just a different formula. Momentum equals h over lambda. Momentum equals 6.63 times 10 to the negative 34 joule seconds divided by lambda 1.36 times 10 to the negative 12 meters. So the resulting momentum turns out to be 4.875 times 10 to the negative 22 kilogram meters per second. And if you can remember, now we have the resulting momentum after. To find the y component, it's going to be sine 15 degrees is going to be equal to the opposite y component over our resultant 4.875 times 10 to the negative 22 kilogram meters per second. So you can remember all of this extra work we had to do when you had momentum at angles. So if we multiply this by sine 15 degrees, you get 1 point, I'm going to go to 3 decimal places, 262 times 10 to the negative 22 kilogram meters per second. Cos 15 degrees is going to equal to px over our resultant again, 4.875 times 10 to the negative 22 kilogram meters per second. So our x component, 4.875 to the exponent negative 22 times cos 15 is going to equal to 4.709 times 10 to the negative 22 kilogram meters per second. So I'm just going to hold tough here and underline these key numbers. My momentum in the x, my momentum in the y, and my momentum before. And we'll do a little quick recap of what we've done so far. Remember, conservation of momentum requires that the total x components before has got to equal to the total x components after. Total y components before has to equal the total y components after. I'm going to summarize all these components once I finish all the different parts. But what I've done on this slide is looked at my X-ray coming in. It was traveling straight east, so I don't have to break it into a component. It already is in a component. It has a total momentum in the x direction before of 5.1797 times 10 to the negative 22. I looked at the X-ray after because I know its wavelength. So if I know its wavelength, I can calculate its momentum. I found the resulting momentum. Then I broke it into its x and y components. The key numbers that I'm going to be working with is this, this, and this. But I'm not finished. The after also includes the electron. So I have to work out the parts of the electron as well and use the appropriate formulas. If we go back to our original diagram, conservation of momentum should tell me that that electron should head southeast so that we have the two y components adding to 0. If I have no y component before, that means the y components after have to add to 0. Then I can find the x component, and I know what the x component of the electron plus the x component of the X-ray have to equal. So if we go to a picture and we work on now the electron after, I just don't have enough room to do that all in one slide. The electron's going to move at some angle south of east, and we don't have any information except for its mass. Mass equals 9.11 times 10 to the negative 31 kilograms. We don't know its velocity. In fact, that's what we're looking for. So we don't know the momentum. But we could figure out the momentum in the x and the momentum in the y, we could then go and find the resultant and then find the angle after, theta. Well, since I know what the total momentum in the x direction has to be, it's 5.1797. 5.1797 times 10 to the negative 22 kilogram meters per second has to equal to the momentum of the electron after plus the momentum of the X-ray after, 4.709 times 10 to the negative 22 kilogram meters per second. So I can find that X component, 5.1797 exponent negative 22, subtract 4.709 exponent negative 22. So we get the momentum of the X component for the electron turning out to be 4.707 times 10 to the negative 23 kilogram meters per second. Do the same with the y. The total momentum in the y direction was 0, and it's going to equal to the momentum of the y direction for the electron plus the y direction for the X-ray was 1.262. 1.262 times 10 to the negative 22 kilogram meters per second. So the y component will then just be the same number, opposite sign. And that should make sense if you remember back to Unit 1. When we're dealing with momentum, these are vectors. So we need to have appropriate directions and signs for that direction. Notice the y component is down, so it should be negative. Now that we know the momentum in the x and the momentum in the y, we can then use Pythagoras Theorem to find the resulting. Once we know the resulting, we can then find the regular momentum. Lots of work. Then when we find the momentum, we can then find the angle. So Pythagoras Theorem tells us that the resulting momentum will be equal to px squared plus py squared square root. Put those numbers in. 4.707 times 10 to the negative 23 kilogram meters per second squared plus negative 1.262. You don't need the negative sign, but I'm putting it in anyway. Negative 22 kilogram meters per second squared, square root that result will have us find the momentum squared plus 4.707 to the exponent negative 23 squared plus 1.262 to the exponent negative 22 squared, square root the result, gives us 1.36 times 10, 1.346, so 1.35 Need my eraser here. .35, I'll keep the actual value on my calculator, times 10 to the negative 22 kilogram meters per second. We know that P equals mv for an electron, so velocity equals momentum divided by mass. We're almost there. 1.35 times 10 to the negative 22 kilogram meters per second divided by 9.11 times 10 to the negative 31 kilograms. Divide by 9.11 to the exponent negative 31, and we get 1.48 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Good. I'm glad it's not faster than the speed of light. Meters per second. These will be very, very fast moving electrons, by the way. We're coming in with very high energy X-rays. So the electrons should be 10 to the 7, 10 to the 8 meters per second. That's a good indicator that I've done this question right. Before I do the angle on the next slide, let me just recap what I've done. Since I've calculated the momentum of the incoming X-ray, I calculated the momentum of the exiting X-ray, found its components. Now the electron's components has to add back to the original. Total momentum in the X before, total momentum in the X after. So the 5.1797 was the momentum of the photon coming in the X direction. The two X directions in the resulting X-ray and the electron have to add to it. That's where my 4.707 times 10 to the negative 23 came from. My Y components have to add to 0 because initially there was no Y component. So the Y component of the electron was equal and opposite sign to the Y component of the scattered X-ray, 1.262. Use Pythagoras Theorem to find the resulting vector. Once you find the resulting momentum, use the momentum of a particle formula to find the velocity. Now that I got velocity, I could go back to another slide and find the angle. Tangent theta is going to equal, if you look back at our diagram, Py over Px. Momentum in the Y, momentum in the X. So the Y component was 1.262 times negative 10 to the negative 22. 1.262 times 10 to the negative 22 kilogram meters per second. The X component, 4.707 times 10 to the negative 23. 707 times 10 to the negative 23 kilogram meters per second. To find theta, you second function that number. So second function 10, 1.262 exponent negative 22, 4.707 exponent negative 23, and you get an angle here 69.5 degrees south of east. Now I rounded those values, but you get the gist of what we're doing here. Should be pretty close to 69.5 degrees as our answer. You could see why I wouldn't put this on a standard unit exam. This is about a 15-20 minute question on its own. Just like back in Unit 1, when we gave you angles, I told you conservation of momentum with things leaving at angles other than 90 degrees is quite a lot of work. You need components, and the key thing you have to remember with all types of momentum, whether it's photons or particles, the total momentum in the x direction is conserved, the total momentum in the y direction is conserved. The biggest mistake students make is they just find resultings and conserve those. That's not the case. Total x before, total x after. Total y before, total y after. Just to remind you, there wouldn't be any of this type of question on your exam, but I will put something like this in your final review package, especially for those of you that are wishing to write the diploma exam. Very common type question. Talks about two different concepts that we've done in this course.